Welcome back, mathematicians. So we are continuing our study of trig identities. And so today's title is More Using Trig Identities. We're on notes number 44. And here's a reminder of all the trigonometric identities that we have been learning how to use. This is the set of 8 fundamental identities. That's what your book calls them, the fundamental ones. And we're going to practice using them again today. So here we go. Factor each trigonometric expression. Okay, so the first 5 examples or so are all going to be factoring expressions, and these all use factoring techniques that we have learned in the past. We're just applying them now to something new, trigonometry, and being able to factor these expressions is going to help you when it comes time for us to solve the equations, which are coming later in this unit. Okay, remember this factoring formula, the difference of squares? A squared minus b squared factors into a plus b times a minus b. Those are conjugates, remember that? Well, that's what we have going on here in this problem. We have secant of theta squared minus 1 squared. We have a difference of squares, okay? Remember, we just don't write the secant of theta squared like this. We write it like this instead, but it means the same thing. Okay, so that means this is going to factor into secant theta, oops, got a little carried away with my c, secant theta plus 1 times secant theta minus 1. Now, hopefully you realize that that plus 1, it's outside the secant function, and the minus 1 is outside the secant function. The only thing that's inside the secant function in this case is theta. Okay, let's take a look at number 2. More factoring, and this also, even though it is scary looking, I will admit it is scary looking, it is just a difference of squares. It's another example of a squared minus b squared, which factors into a plus b times a minus b. So we have something squared minus something squared. So we have green squared minus blue squared. So that's going to factor into green plus and minus blue. All right, that's all it is. So we have tangent x plus cotangent x, green, plus tangent x minus cotangent x, blue, times tangent x plus cotangent x, green, minus tangent x minus cotangent x, blue. Now let's see what we can do to simplify each of these. So notice in the first factor, there is a plus cotangent x and a minus cotangent x. Let's cancel those. And we're left with tangent x plus tangent x. So that's 2 tangent x. Notice in the next one, oh, I almost made a very big mistake. I hope you see that. Remember, when we're subtracting a quantity, we need parentheses around that quantity because we need to remember to distribute the minus sign. That would have been catastrophic. Okay, so let's go ahead and simplify that one. So it is tangent x plus cotangent x. Now I'm going to distribute the minus sign. Minus tangent x plus, from minus minus, cotangent x. Okay, now let's look at that. Notice that we have a tangent x minus a tangent x. Those cancel. And what we have left is cotangent x plus cotangent x, 2 cotangent x. So we have 2 tangent x times 2 cotangent x. Do you know what tangent x times cotangent x is? I hope you do. Remember that these are reciprocals, and what happens when you multiply reciprocals? You get 1. So we really just have 2 times 2 times 1. We have 4. Okay. So factoring turned into just a single number, it looks like. Next one, number 3. Factor each trigonometric expression. Okay, this expression looks like this kind. It looks like 4x squared plus x minus 3. It looks like a trinomial. And if that was the problem, then we could factor it into, let's see what that would work out to be. Let's try 4x and x. Let's try 3 and 1. Let's try minus 3 and plus 1. Okay, those would be the factors if there was just an x there. But instead of an x there, there's a tangent beta there. Maybe you remember in the beginning of the year when we did factoring by substitution. So in this, you could think of this as substituting x in for tangent beta. So this is going to factor into 4 times tangent beta in the first one, and tangent beta in the second one. And then we have a minus 3 in the first one and a plus 1 in the second one. So when you check this by doing the FOIL process, notice the inside gives you minus 3 tan beta, and the outside gives you plus 4 tan beta, and those do add to just 1 tan beta. Okay, so we have our factors. Okay, let's look at number 4. This one is also kind of like a quadratic. However, instead of to the second power, it's to the 4th power. That's okay, we can treat it like a quadratic. Remember when I used to call them quadratics in disguise? We're going to treat it like a quadratic. So to get cotangent to the 4th, we're going to do cotangent squared times cotangent squared. And then to get the last to multiply to give us 2, how about if we have 2 and 1? If we have a plus 2 and a plus 1, then the insides and outsides will add up to 3. 3 cotangent squared theta. And so that is now factored. Number 5. Okay, this one should remind us of something like this. A cubed plus b cubed. It's a sum of cubes. And we have a special factoring formula for a sum of cubes. It's a plus b times a squared minus ab plus b squared. Remember the SOAP formula? Same, opposite, always positive, referring to the signs. Okay, so this problem is the sine of alpha cubed, we just don't write it that way, plus the cosine of alpha cubed. So sine of alpha is our a, and cosine of alpha is our b. So the first thing we get is a plus b, sine alpha plus cosine alpha. And the next thing we get is a squared, sine squared alpha, minus ab, so minus sine alpha cos alpha, plus b squared would be plus cosine squared alpha. Okay, so it's factored, but there's a little bit more we can do to simplify, because in the second factor we have sine squared alpha plus cosine squared alpha. And what is that? You're right, sine squared alpha plus cosine squared alpha is 1. So let's replace that part of it with 1. So our first factor is still sine alpha plus cosine alpha, and our second factor is 1 minus sine alpha cosine alpha. Okay, awesome. Now we move on to part 2, and the directions have changed. So this one says, each expression simplifies to a constant, a single function, or a power of a function. Use fundamental identities to simplify each expression. So this is similar to what we did in our last homework assignment last time, where we used these identities that you see on the right side, and we did substitutions until we had it simplified as much as we were supposed to. So we're doing that same thing again. And so we're going to replace cotangent alpha with, let's see, not that one. Let's replace cotangent alpha with this one, cosine alpha over sine alpha. So we have cosine alpha over sine alpha times sine alpha. Why did I choose that one? Because I wanted the sine alphas to cancel. So what is left? Cosine alpha is left. Is that either a constant or a single function or a power of a function? Yes, it's a single function. It's cosine alpha. So there we go, simplified. Here comes number 7. Same directions. So Let's change everything into sines and cosines. So let's replace cosecant theta with 1 over sine theta. Let's replace secant theta with 1 over cosine theta. And let's replace cotangent theta with cosine theta over sine theta. Okay, now let's see what we can do with this. So let's change the numerator to a single fraction, 1 over sine theta cosine theta. And then let's multiply by the reciprocal of the denominator. So the reciprocal of the denominator would be sine theta over cosine theta. Okay, does anything cancel? Looks like we have sine theta on the top and sine theta on the bottom. We can cancel those. Now what do we have left? We have 1 over cosine squared theta left. Okay, remember we're trying to get this to simplify to be a constant or a single function or a power of a function. Okay, so we could change 1 over cosine back into secant, and since it's squared, we would have secant squared. So we have secant squared theta, and that is a power of a function. So we went as far as we needed to. All right, let's take a look at the next one. I think we have about 4 more. Express as a constant, a single function, or a power of a function. Same thing. Okay, so does this look familiar? Anytime you have something like this, you should be alerted to the possibility that you're going to use a Pythagorean identity. We have those down at the bottom. Perhaps we're going to be able to rearrange this third one. Let's see what we can do. So if we start out with 1 plus cotangent squared theta equals cosecant squared theta, and if we subtract 1 from both sides of that equation, we have cotangent squared theta equals cosecant squared theta minus 1. We could put a t in there instead of a theta, so we're going to replace our cosecant squared t minus 1 with cotangent squared t. And that is a power of a function. So there we go. Here comes the next one. Same directions. All right, so what if we replace 1 over tangent squared theta with cotangent squared theta? Because we know that 1 over tangent theta is cotangent theta. Let's square it. So this would be cotangent squared theta plus, now what is the product of cotangent times tangent? We know those are reciprocals, so the product is 1. Now we have cotangent squared theta plus 1. It is not yet a constant, a single function, or a power of a function. But let's take a look at those Pythagorean identities again. 1 plus cotangent squared theta, that's what we have, is equal to cosecant squared theta. Now it's a power of a single function. So that one is done. Okay, let's take a look at number 10. Same directions. I want you to stop and think about what you would do here. You have a plan? Are you thinking what I'm thinking? What is 1 over secant theta equal to? The reciprocal of secant is cosine. You can use theta or x or whatever. So 1 over secant squared theta is cosine squared theta. So we have 1 minus cosine squared theta, actually x. 1 minus cosine squared x. Okay, does that look familiar? Look at your Pythagorean identities. I bet we could take this one, the main one, and we could rearrange it. If you subtracted cosine squared theta from both sides, you would have sine squared theta. sine squared theta equals 1 minus cosine squared theta. So that means we can replace 1 minus cosine squared x with sine squared x. And that is a power of a function. Ta-da! Do we have any more? Nope, that's it. Cool. Okay, so what you can expect is that basically every example I did corresponds to a problem you're going to do. So when you do 13, you can look at example 1, and when you do 15, you can look at example 2, and when you do 17, you can look at example 3, and so on and so forth. Okay? Be sure to check your answers, and there is a homework solution video in case you need help. Thanks, everybody.